So most of what I am going to talk about today is from this paper of Bloomberg, Cohen, and Schlichtrule. I think it came, I think it was published around 2009. So recall, we had this R module Thom spectrum functor from top over BGL1R to R mod. Okay. So basically we have a space mapping to BGL1R yields a Thom spectrum, which is an R module, which I wrote as THR of F. And this Thom spectrum, so we wrote down a bunch of properties. One of the properties was that THR is symmetric monoidal. A consequence of that is that if so if F is a loop map, that means if there is Y some G to the square GL1R such that omega G is F. So that means what? That means X is the loop space of Y and the map F is the loop. So this already includes that X is the loop space of Y. Okay? So if this happens, then that tells you that this Thom spectrum is an R algebra, associative. And if this was an infinite loop map, the Thom spectrum is a commutative ring spectrum. And on the other hand, if this X F BGL1R, if this is an infinite loop map, then the Thom spectrum is a commutative R algebra. Okay. And we were already assuming that R is a commutative ring spectrum. Okay. So here, so the main argument that I want to explain here is that there is a formula for this. So in these cases, a formula for THH in R modules of this THR of F in these cases as a Thom spectrum. Okay. And then you can use this formula to try and calculate and get an answer. So this is what the main argument is. So let's see how to, so how one can arrive at such a formula. Well, remember that, so if I were to do THH R of the Thom spectrum, so this is the realization of the cyclic bar construction on THR of F. Okay. Right. So because so we have seen this many times that if you have a symmetric monoidal structure, that will take the cyclic bar construction to the cyclic bar construction. So as the Thom spectrum functor is symmetric monoidal, if I take this cyclic bar construction of THR of F, this will be equivalent to the Thom spectrum of the cyclic bar construction on F. But what does that mean? What is the cyclic bar construction on F? Well, so you have to go back to what is the symmetric monoidal structure on the left hand side. So roughly speaking, if your BGL1R was commutative, the monoidal structure is like taking the product of the maps and then using the multiplication on BGL1R. And then you have to somehow manage the situation in the case of a E infinity space. So this cyclic bar construction on F, you can think of it as a map from, you take the cyclic bar construction on X. So first of all, because X is omega y and the map is a loop map, if you can replace both sides by a topological monoid replacement, then this gives you a map from the cyclic bar construction on X to cyclic bar construction on BGL1R. And now you are supposed to multiply, because that's what the monoidal structure on maps is, and this goes to BGL1R. So if you think of, if you have a commutative model for this BGL1R, then this is like given by level wise multiplication. So let's call this, let's call it M. This is like level wise multiplication. Except that it does not work in a very strict sense, because this BGL1R is only an E infinity object and it's not this strictly commutative object. So what is done in this paper of Bloomberg, Cohen, and Schlick rule, they actually described two ways of addressing the situation, but I don't want to go in there. So they give us two ways of writing these E infinity objects in topological spaces, as they replace the category of topological spaces by something which is in which the E infinity objects give you strictly commutative objects. So there are two solutions to that. One involves this use of star modules, which is closely aligned to the S modules, which is described in EKMM. The other one is described using I spaces, which is closely aligned to the symmetric spectra. But I don't want to go into the technical heart of the matter, but for this lecture, you just assume that this level-wise multiplication works. It actually gives you a map of simplicial objects, and so basically this technology allows us to view objects like this as kind of strictly commutative objects by changing the model. Okay. So this is my, so morally this is the cyclic BCY of F. Okay. So that is step 1. And step 2 is that Thom spectra, the Thom spectrum functor commutes with homotopy colimits, commutes with homotopy colimits, and hence geometric realization. So we can also move the geometric realization which we have here inside this Thom spectrum functor. So that implies that PHH R mod Thom spectrum of F is equivalent to, now the realization comes outside, sorry, the Thom spectrum comes outside. Okay. So what is this now? This one is the realization, here, this is the realization of, this goes from the realization of cyclic bar construction of X to realization of cyclic bar construction on BGL1 R to okay. Good. So this composite is the map BCY of X. Now we know that this is equivalent to the free loop space on Bx. So that gives us a formula for the topological Hochschild homology, again as a Thom spectrum. So we get PHH of the Thom spectrum of F is the Thom spectrum of this CY of F. Okay. But still, to make this computationally useful, we have to identify what this map is in a slightly better form. So let's do that. So now we seek to identify what this map is. So first of all, you realize that this is a map of monoids. So you can write this as a composite in this form, LBX to LB of BGL1 R, which is P loop space of B square GL1 R to BGL1 R. Okay. So basically, you need to understand what this arrow is in a better form. And now you see that this is an infinite loop space. So there is something which I did not do earlier. So remember, for the free loop space, if you take LZ, we had this fibration sequence, and then we had a section S. But now if Z is a monoid, then we actually have a equivalence. Lz is z cross omega z. Why does it help if z is a monoid? Well, you can take a loop gamma and an element in z, let's call it little z, and you can send it to t goes to the loop, t goes to little z. Now you can use the multiplication and you can send it to the loop t goes to z times gamma of t. And you can verify by taking pi star that this is a weak homotopy equivalence. So if z is a monoid, then we have this situation. Okay. Now this b square GL1R, this is a BGL, this is an infinite loop space. So in particular, there is a, it is homotopy equivalent to a topological monoid. So we have this kind of decomposition for L b squared GL1R. So in particular, now we have L b squared GL1R. This is homotopy equivalent to a product BGL1R, which is the loops on this b squared GL1R cross b squared GL1R. Okay. So now let me state the theorem. Which was Bloomberg and so they now identify what this map is. So if you have f, so let's say g goes from y to b square GL1R. So now you are trying to calculate the THH of the Thom spectrum of omega g. So the formula is THH of the Thom spectrum of omega g is equivalent to THR of the Thom spectrum of, we write it as L eta g, where this L eta g, so eta stands for off map S3 to S2. Okay. So L eta g is given by the composite free loop space of y goes to free loop space of b square GL1R, which is equivalent to BGL1R cross b square GL1R. Now there is identity cross eta upper star goes to BGL1R cross BGL1R, and then you use the multiplication to get to BGL1R. So this entire composite is denoted by L eta of G. Okay, so eta upper star comes from the following. Oh, yes, thank you. THHR. Y is a space. You don't need any assumption on y. So we'll see in the examples, like we will apply it to a bunch of examples and then we will see what kind of answers you get. Okay, so here, what is this eta upper star? Well, this eta upper star is a map from B square GL1R to B GL1R, and basically what you use is that this is an infinite loop space. In particular, this is a double loop space. So double loop space, I can write it as map from S2 to B to the 4 GL1R, and now I can pre-compose by eta. So this is actually eta upper star. This goes to map S3 B to the 4 GL1R, and that is equivalent to BGL1R. Okay, so that is what eta upper star is. Okay. So what I have described so far is how to. So what you have to do is you have to identify this realization of BCY of F with what I wrote here as L eta of G, where F is omega G. Okay. So that's what you have to do. Okay. How does one do that? So you have to go back to the equivalence of the cyclic bar construction with L. So remember, so instead of writing, so we write now G for, we will write G to denote BGL1R, okay? Because that's, otherwise the notation is going to get a bit complicated. So we have here B Cy of G, and that maps to the free loop space of BG. This goes to BG. This goes to BG. So we had this diagram, omega BG, which is G, and the fiber here is G. So we had this diagram which basically showed that the cyclic bar construction on G is LBG. Now the map that we are looking at is the level-wise multiplication map from the cyclic bar construction to G. Okay, and from this simplicial description, it is clear that this map is the equivalence. Yeah, realization, sorry. Okay. So that map is an equivalence. Now here, what are we trying to do? So we have BG cross G, and and we are trying to see what, so this is an equivalence. So let's say this is gamma. So we are going to look at gamma inverse followed by this map which I called M. So basically you want to understand the map M circle gamma inverse, and you want to identify it by this guy. Okay, that's what you want to do. Okay, so now there are some observations which you can make over here. So in this case, G is an infinite loop space, and you see that all these maps are infinite loop maps. Also, there are all these there is this retraction by the constant loops R. So all these maps are actually maps of infinite loop spaces. So we can think of it as maps between the corresponding connective spectra. All the maps come from maps of infinite loop spaces. So let's write now G for the connective spectrum of capital G. So write it like this, and so then you see that the omega infinity of the suspension of G is Bg. And so this we can now write it as the following. The one on the bottom you can think of as map S1 plus suspension of, or write it as S1 smash G. This is S1 smash G, or the suspension of G, and you have this constant map. So it goes like that. This is G, this is G, this goes as a cyclic bar construction on G. This goes to S1 smash G. And here I'm using M goes to G. Okay. So here, so basically we are looking at M circle gamma inverse, and so as spectra, this is the wedge of these two. So this because M circle gamma inverse comes from this infinite loop map, we just have to study the map on each individual factor. So now if I write this as, so I have to analyze this M circle gamma inverse. This is the map of spectra now. This is map from S1 plus S1 smash G to G, but this side is given by, this is the wedge of these two factors, G wedge S1 wedge G, S1 smash G, and the splitting is given by this by this constant section. So now this M circle gamma inverse is specified by, so this is specified by two maps. G to G and S1 smash G to G. How do you calculate the maps? So how is this split into this wedge? You take this plus you take this constant loop and then you wedge, and then you get a map out of the wedge to this factor. So to go, so for on the factor G, you have to go like this and you go end up here, but that is equivalent to going via this. So this map here is equal to identity. So the only thing that is to be figured out is the other map where you go like this, you apply gamma inverse and then you follow it by M. Okay. That's the only thing that has to be figured out. So you have to figure out the following map that you go from S1 smash G to map S1 plus S1 smash G to the cyclic bar construction on G, and then you have this level-wise multiplication onto G. So this is the map you have to figure out. Well, now here you observe, if I now take the cyclic bar construction on G, well, what you were, so this is the, so here in this cyclic bar, so I'm looking at the G as an infinite loop space, and I'm trying to build up the cyclic bar construction on the infinite loop space, which on omega infinity gives you the product. So that is the categorical, this cyclic bar construction is calculated using the categorical product on spectra, and at each level, you get a finite product which is equivalent to a finite wedge. So here, the spectrum I have here is like the realization of G, G wedge G, and so on. You get that. So this you can rewrite as G smash, you have 1 point, then 2 points, then 3 points, and so on. So at level n, you have n plus 1 points. And this realization is the same as S1 plus. As a simplicial set. The simplicial set where at level n there are n plus 1 points. You can work out with the simplicial identities that this is like, so you have, okay, I'll not, this becomes equivalent to the S1 plus. Okay. And so what you have to do is the following. You have to look at, so let's look at this map then. So you have map S1 plus S1 smash G to S1 plus smash G, and you have to go down to G. So you send, so this M here, this will be sending it to the, from S1 to the non-base point. So you have to identify G with S0 smash G, and then you get that. Okay. But even over here, I can write this as map S1 plus S1 smash G. So the entire thing is determined by to S1 plus to S0. Okay. This entire thing smash G. It's that composite smash G. Okay. And now over, oh sorry, I messed it up. No, this is fine. Okay. Okay. Wait. Oh, I also have this one, right? So you also have, sorry, I also have to look at this one. So S1 to that. So S1 to that composite. Okay. Now you can figure out the map from S1 to map S1 plus S1. This is adjoint to S1 smash S1 plus to S1, and this is given by the, this is induced by the multiplication by the product on S1. So you figure out that this is induced by the product on S1, and here what we are doing is you are looking at this. So what the second part of this map does is you have this map S1 plus comma S1 is S1 wedge S naught, and you're looking at the factor which maps to S naught. How do you identify which factor goes to S naught? Well, for that you just do the Hopf construction, and so to figure out this, so this composite then is determined by the Hopf construction, and you remember that if you do the Hopf construction on the multiplication on S1, you get eta, and thus we get eta from S1 to S0. Okay. So that so those are the basic steps which identifies this map as eta smash identity. Okay. Good. So if that is eta smash identity, now you go back to what happens on the level of infinite loop spaces. So on the level of infinite loop spaces, you get that this, so we have L BG to G, and this is equivalent to G cross BG, and on infinite loop spaces this goes like this, because on as spectra they map as wedges, wedge of identity and eta smash identity, and so the first factor is identity and the second factor is eta smash identity. So eta smash identity on BG exactly induces this map eta upper star. So that is identity comma eta upper star, and then you use the multiplication. So that gives you a way of identifying this map as L eta of G. Which one? Eta star is this one. Oh, because here I have this identification, right? So what did I say? I said that in entire everything is over here is like a map of infinite loop spaces. So you write it as omega infinity of some spectrum, and you figure out the spectrum level maps. And then I wrote down what the spectrum level maps are. Okay, so now this is G cross BG, and the map goes like okay, so it's like you take the wedge of spectra and then you take the fold map, yeah, and then if you apply omega infinity of that, it's like a product going to a product, and then you apply the multiplication. That's what we have over here, product going to product, and you apply multiplication. So the identity will give you identity from G to G, and then eta wedge identity gives you, sorry, eta smash identity gives you eta upper star from BG to G. That's what I'm saying. Okay. All right. So we have this situation. Yes. See, my definition of So this little GL1R was always connective. And the G, when I defined it just over here, G is like the suspension of GL1R. Okay, so now let's come back over here. So there is a continuation of this theorem, which is special cases. Okay. So special cases is that if G is a loop map, so that means if G is a loop map, that means that the map defining the Thom spectrum is a double loop map. Okay, so if G is a loop map, then I have a simplification of this THH R of omega G is going to be R of omega G smash over R EH R of eta circle G. Oh, sorry, now there are too many G's, but we will not use little g anymore, so it should be fine. Okay. So what is happening here? What is so see, G goes from, so what is eta circle G? Or eta upper star circle G? We should write it like this. So we have y to b square GL1R. This is my G. And now I compose it with eta upper star that goes to BGL1. So this is eta upper star circle G. Okay. So this is special case 1. And special case 2 is if G is a double loop map, so that means that the Thom spectrum is now a triple loop map. Okay, the map defining the Thom spectrum is a triple loop map. Then even simpler, EHHR of the Thom spectrum of omega G is equivalent to the Thom spectrum of omega G smash Y plus. Okay, so let's see why these things are true. So how does one observe these cases? So for the case 1, so we look at the formula. Okay. And the important thing in this formula is this splitting here. L b squared GL1R is BGL1R cross b squared GL1R. And what does this splitting rely upon? This relies upon a monoid structure on the space b squared GL1R. So if this G is a loop map, then the map from Y to b squared GL1R, that means you can refine it to be a map of monoids. So that means the map Ly to L b squared GL1R, first of all, Y will also have this kind, Ly will also have this decomposition, and the map from Y to b squared GL1R will actually commute with the decomposition. So if G is a loop map, this implies that I can actually write the following. This is LG, the map induced by G on free loop spaces, but now they are going, this is going to commute with this omega B square GL1R cross B square GL1R. This is going to be omega G cross G. So this diagram is going to be homotopy commutative if G is a loop map. And now what you do here is you go to identity cross eta star to BGL1R cross BGL1R M BGL1R. Okay. And so now if you look at this via this equivalence, if you look at this composite, well, this is exactly what I wrote as a box product. So this map is nothing but omega G box cross eta star circle G. And then the fact that the Thom spectrum is symmetric monoidal implies that the Thom spectrum of omega G box cross eta star circle G is EHR of omega G smashed over R THR of eta star circle G. Okay, so that verifies this case 1. For the case 2, one has to make a small maneuver and then it is fine. So now let's come to the case 2. We'll make a small maneuver. I will define a map from Y cross BY. Sorry. Y cross BY, but omega Y cross Y to omega Y cross Y. And here this will be given by identity star eta upper star identity. Okay. So what does this mean? So this means that the factor omega Y, so this is a map omega Y cross Y square, and then you use the fact that Y is a loop space to multiply and come here. Okay. So the first factor goes in by identity comma base point, and the second factor goes in by identity on the second factor and eta upper star on the first factor, like we had before. So now you look at how eta upper star is defined. To define eta upper star, we had to write eta upper star. So eta upper star goes from Y to omega Y, and this is defined as map from S2 to map S3. Okay. So this is why, so to define this eta upper star, you need Y to be a double loop space. Not only that, if G is a double loop map, then this construction commutes with the analogous construction on B square GL1R. Okay, so this also commutes with the construction with the same analogous construction on B square GL1R, if this is a double loop. And now if I take the projection onto the first factor, and now if you calculate this composite, you see that this composite here is, so this is first of all the free loop space of Y. This composite is same as taking L eta of G. That is because we have put this eta upper star in this thing. Not only that, the way we have defined this map, you can easily calculate on homotopy groups to see that this is a weak equivalence. So that means that L eta of G is equivalent to this particular map. This implies L eta of G. So the Thom spectrum of this L eta of G is equivalent to this particular map, but this particular map is nothing but omega G cross identity cross G, but now you are taking projection onto the first factor, so that means this is THR of omega G box cross the constant map, so that is THR of omega G smash Y plus. So that's the second special case. Now let's do examples. So the first example is, we know that if you look at BU to BO and you go all the way to BGL1S, and let's call this map F, then we know that I will not write the decoration here because it's a sphere spectrum. The Thom spectrum of F is MU. It's the same thing. It's the same thing here. No, V squared GL1R. It's like this. Oh, I think this is good enough for us. So that's why we don't have to further look at the thing, because you'll see in the examples. See, now this Thom spectrum of F is mu, but now we can apply the formula for the topological Hochschild homology of Thom spectrum. So we have THH of mu, which is this, which now okay, so to calculate this, you see this we know is an infinite loop map. So it definitely is a threefold loop map. And so this special case 2 applies. So what will the special case 2 say? This will say that this is mu smash B of BU plus, but B of BU plus is nothing but SU. So this is the direct limit of the SUNs. And now if you just, you know what the homology of SUNs are, you just have to believe that the same formula works over mu, and then you get the uh, answer which was there in Gabriel's talk. So so you know that you just have to remember that this is isomorphic to exterior algebra on x1, x2 with mod xi equal to 2i plus 1. And that gives you the formula. Okay, so that's and now you can see there are plenty of other examples of this type whose THH you can calculate. So the next thing is we had the formula for Fp. So for the formula for Fp, we had omega 2 S3 to BGL1 SP. This was my mu p tilde, and the Thom spectrum of mu p tilde was HFP. And so this was constructed as the free E2 map. So this is a double loop map. So we are in this special case 1. We are in this special case 1. And here, what do we get? We have, from there, we have THH of Fp is HFP, which is the first factor, smash the Thom spectrum of, you see, eta upper star circle some G P tilde, where this Gp tilde is from d of omega 2s3 to b square gl1 sp. But this is omega s3. Okay. But now we can now do a maneuver because we have this HFP plus. So this TH of eta upper star circle GP tilde is going to be equivalent to, so to get this HFP smash this, we have to go all the way to the units of HFP. So this is the Thom spectrum of omega S3 to B square GL1 SP hat to BGL1 SP hat to the units of FP. So that's like K Z mod KFP cross 1. Okay. But omega S3 is 1 connected. So any map from this to K's FP cross 1 is null homotopic. And for a null homotopic map, we have this is HFP smash omega S3 plus. Okay. So that tells you that, so this is the same formula. HFP smash, yeah, oh sorry, I have this. HFP smash This is the Thom spectrum of the composite. Thank you. So we get that THH star of Fp is isomorphic to Fp star omega HFP star omega S3, but HFP star omega S3 we know is Fp with some mu with degree mu is 2. Okay. So maybe I'll in a second I will say what happens for Z, and then I will stop. So for Z, you can maneuver around this argument to get an argument for Z. So basically, you look at S33. This is the 3 connected cover of S3. And now if you look at omega 2 of this 3 connected cover to omega 2 S3, and then you use the map mu p tilde, and let's call this chi, to BGL1 SP, then the Thom spectrum of the composite which is mu p tilde circle chi is HZP, the Eilenberg-MacLane spectrum, so the completed Eilenberg-MacLane spectrum. And again, the same argument with the double loop maps and everything happens, and you can see that THH of HZP is going to be equivalent to HZP smash omega S3 3 plus. Okay, so you have to see what the homology of this 3 connected cover is, and you get to THH of HZP. Now, what about HZ? Well, you have all these maps from, so for each prime P, you have these maps omega 2 S3 3 to BGL1 SP, and let's call this some GP tilde. Okay, so for each P you have these maps, and this right hand side you can view as BGL1 no, you can not only that, this actually goes to the connective cover, because this omega 2 S3 3, the it is 0 connected. So this goes to the connective cover, which I write as B SL1 SP. Okay. And now you see that this B SL1 SP, this is same as the P completion of BSL1S. Not only that, this space here, BSL1S, it has all the homotopy groups are finite abelian groups. So if you take the rationalization, you will get just trivial space. So Now, if you remember the fracture square, which I think was written by Wiglek in the first lecture, but yeah, so from the fracture square, you see that given maps like this to the P completion for each prime P, you can use them to construct a map actually to BSL1S. So you get a map. So all these G tilde P, they come from a map from omega to S33 G tilde to B SL1S. Now you go all the way to BGL1S and you take the Thom spectrum of G tilde, and whatever this Thom spectrum is, you know that for after any P completion, you get the Eilenberg-MacLane spectrum HZP. Not only that, you can calculate that pi 0 is Z. So you have this map from the Thom spectrum to HZ, which is a equivalence after taking every P completion. So that tells you that this is HZ. Further, you need a little bit of an argument, and you can say that because all of these are double loop maps, that will imply that this one is also a double loop map. So basically you have to deloop twice and you have to consider the scenario there. So this also becomes a double loop map. And then the arguments we have there tell you that THH of HZ is equivalent to HZ smash omega S33 plus. And this homology again you can calculate using the shared spectral sequence, and you will get that THH star of HZ is Z if star is 0, Z mod I if star is 2i minus 1, and 0 for, of course, I, which has to be bigger than equal to 0, and star even greater than 0. Okay, I think I will stop there.
Are there any questions?
Yes. Oh, the mu, so is the generator in degree 2. So, you know the homology of omega S3, the Pontryagin ring. It is a, so omega Sn, the homology is, yeah, but here it's Fp, so you will get Fpx. Okay. I don't think so, because the K theory doesn't, but I guess the connective K theory is doesn't arise, but okay. It is. Okay. Yeah, I mean, over other ring spectrum, it could be possible to construct it, but I don't know. Perhaps not over this. Yeah. Yeah, yeah.
Any further questions?